I'm Ali Safa, so I'm from imec and the KU Leuven. And here in this work, I will present to you a work we did where we are exploring basically the use of Metropolis-Hastings sampling as a Bayesian inference technique for inferring the weight of a spiking neural network in a model-free manner. And that could be used, for example, in chip-in-the-loop kind of training procedures of emerging computing technology. This work was done together with my colleagues here at UC San Diego as well. So as I said, the goal of this work was to explore Metropolis-Hastings sampling for doing a kind of model-free training of spiking neural networks. And really the motivation behind this is the fact that, as we know, spiking neural networks have gained a huge attention for building, let's say, the next generation of ultra-energy efficient kind of AI systems, for example, for applications such as personalized healthcare and IoT and so on. And certainly a general kind of promising path for building the hardware needed for these SNNs is through the use of less conventional hardware techniques, so beyond, let's say, digital computing. So perhaps using analog subthreshold designs, using memory stores, using phase change memory, and so on. And because of the kind of increased variability of these let's say, emerging technologies, and we saw a number of talks, in fact, that were, let's say, discussing this in this conference. Because of this increased variability, often we don't have a perfect kind of knowledge of the model of how these kind of spiking neural network hardware that we are designing are working precisely. And so that's why works have been looking into the use of chip-in-the-loop training techniques to, let's say, train these systems. That's what we are also looking into this work here, where we are considering the following setup here. We are assuming a certain spiking neural network that is subject to unknown hardware non-ideality in our kind of simulation setup. And we will compare basically the use of Metropolis-Hastings sampling, which is a model-free kind of approach, against the use of, let's say, surrogate gradient backprop, which I would say most of us are quite familiar with. So before getting into, let's say, our methods, I wanted to give perhaps a short recap on how we can, in fact, leverage the Bayes rule in order to train neural networks. So basically, we can do it as follows. So here you can see on the slide the well-known Bayes rule that we kind of all know from let's say, our studies. And what we see here is that we can infer a posterior distribution over the weights of a neural network, given the training data here, D, by simply using the Bayes rule, which basically says that this posterior distribution is equal to the product of the likelihood of the data given the kind of weights of your neural network or the model, times the prior belief that you have over how these weights are distributed, divided by the probability of the data itself. And so this Bayes rule can be used, in fact, to gradually learn the probability distribution of the weights of a neural network, given the data, given the training data that you're receiving, by basically using the posterior that you infer at time step, for example, n+1, as the next prior in the next kind of iteration step that you could take in your kind of incremental Bayesian learning. Now, this works, of course, quite well when your model has a few parameters, but when you start having a lot of parameters, the problem is that tracking probability distributions that are quite highly dimensional, for example, in the neural network, we have hundreds, if not thousands, or even more weights, of course, then it becomes quite computationally expensive. That's why in literature, we often use sampling techniques in order to, let's say, try to find a posterior distribution of the weights of a neural network given the data. For example, let's say, a quite used kind of technique here is the so-called Metropolis-Hastings sampling technique. So this technique allows you to retrieve samples that exactly come from the posterior distribution of the weights here in this case of a neural network, given the kind of training data that you are using. And so I will walk you through how this Metropolis-Hastings sampling algorithm works here quickly. So let's say we have initialized the system with a previous kind of weight tensor W at time step n-1 here. So this W is a kind of a tensor that contains all the weights of your neural network. What you will do as a first step would be to sample a new proposal kind of weight tensor WP using a normal distribution centered on the previous weight tensor that you have. Then you need to check if this newly proposed weight tensor WP, in fact, corresponds to the posterior distribution of the weight given the data. So should it be accepted as a sample that comes from the posterior distribution that you're finding, or should it be rejected, like the red, let's say, dots that you have here? To do this acceptation and rejection kind of step, what we do is that we will, in fact, first compute the likelihood of the data given the newly proposed weight tensor WP. We also have in memory the likelihood of the data given the previous weight tensor WF times step n-1 here. And then these two likelihoods, in fact, by the way, we find them by running the neural network in a forward pass. And then we will use these likelihoods to compute a so-called likelihood ratio here that you have at the step 3 here, which will give you this quantity P. So this quantity P is in fact a ratio between the likelihood of the data given the, let's say, the newly proposed weight tensor WP times the prior probability of that, let's say, newly proposed weight tensor WP, divided by the same quantity, but computed using the previous weight tensor. And then what you do is that you consider this P quantity here as, in fact, a probability of acceptance and rejection. So you will accept the new kind of weight tensor WP that was proposed with a probability small p here. So you will basically toss a coin with probability small p of success, and you will accept or reject that WP as a kind of weight tensor sample that comes from that posterior probability distribution. And by doing that, you will get a collection of samples that are accepted here in blue, as you see. And if you take the histogram of that, basically all these samples, you will in fact retrieve the posterior distribution of the weight given the data. So now that we saw how Metropolis-Hastings work, let's go into, let's say, understanding how our methods work and certainly how we build our spiking neural network kind of simulation setup. So in this work, we will use leak integrate and fire neurons in our SNNs, but what we will do, quite importantly, is that we will modify the leak integrate and fire neurons so as to introduce a kind of simulated non-ideality to the kind of hardware that we have, that we're kind of simulating here. The idea here is that we introduce a form of distortion on the membrane potential of the leak integrate and fire neuron by using this kind of nonlinear function. This function is an arbitrary hard kind of nonlinearity, so you can make its nonlinearity degree harder and harder by increasing sigma, this hyperparameter sigma here. It has this term to the squared and a term to the third. And what we'll do basically in our experiments that we will study the kind of behavior of Metropolis-Hastings for training this SNN as we increase the non-ideality degree of the leak integrate and fire neurons, let's say with regard to the kind of standard way a leak integrate and fire neuron should work. And we'll compare that, of course, to the backprop setup, as I said. Now, in this slide, we see how we integrate the spiking neural network into the Metropolis-Hastings algorithm. So here on the bottom right side, you have in fact the Metropolis-Hastings algorithm that is shown here. So the first step, as I said, was to kind of get a proposal weight tensor WP. And then you need to compute the likelihood of the data given this newly proposed weight tensor WP. To do that, we run the spiking neural network that we have in our experiments in a forward pass only. And so here in this case, we are using, in fact, data coming from the Wisconsin breast cancer detection dataset. So we have basically spike trains of dimension 30 here that are, let's say, Poisson encoded. We run them through the spiking neural networks, which has, let's say, two outputs that indicate the presence or absence of cancer detection in this use case. And what we are trying to do is that we are trying to steer the output rates of these leak integrate and fire neurons here to correspond to the one-hot encoded label that we have. Now, we need to compute a likelihood function. Here, in this case, we choose a kind of classical Gaussian likelihood model. But of course, as we know, the Gaussian likelihood model corresponds, in fact, to a mean square error loss. So if we take minus the log likelihood of a Gaussian, we get a mean square error. And so what we can do is to compute the mean square error between the labels and what we obtain as response of the spiking neural network by just running it in the forward pass. And then using the mean square error in let's say, in the exponent of that Gaussian likelihood. And then we can use this likelihood in the Metropolis-Hastings algorithm in order to basically sample, let's say, weight samples, obtaining a lot of weight samples that come from that posterior distribution. We can track indeed their kind of accuracy of each sample that we have on the train set that we have, and then choose the ones that, let's say, achieve higher accuracy and then use them in the testing case. Now, let's move towards our results that we obtain in this algorithm. So as I said, the goals of our experiments were kind of twofold here, really. So the first kind of principal goal was to see how this Metropolis-Hastings technique is robust to the non-ideality of the spiking neural network compared to backprop. And also we wanted, in fact, to quite interestingly study the data efficiency of this Metropolis-Hastings training technique compared to the backprop setup. Meaning by data efficiency, we really mean how much training data points do you need to achieve a usable test accuracy. So in all our experiments, we do a 5-fold kind of train test procedure. So you will see basically the average accuracy and the standard deviation always kind of reported. And for the backprop case, what we do is that we use a Gaussian surrogate gradient with the Adam optimizer in this case. So here you can see, in fact, the first result that we obtained here. It's in this graph, you can see the test accuracy of the spiking neural network in function of this distortion strength sigma. That sets basically the non-ideality degree of the spiking neural network that we have. What we see, quite interestingly, is that as we increase sigma, the backprop trained system will lose its accuracy gradually. And this comes, of course, from the fact that in the forward pass, then your SNNs will have kind of a behavior that is different from what the surrogate gradient setup has, let's say, that is using for doing the backprop per se. But of course, in the Metropolis-Hastings case, because it's a model-free kind of technique, we of course would expect it to be more robust, and this is also the case. We see that the Metropolis-Hastings case does not really, is not really affected, in fact, by the varying hardware non-ideality kind of degree that we simulate here. But still, quite remarkably, we see that surrogate gradient is, in fact, quite resilient because it kind of keeps its accuracy up to sigma equals 2, but really decreases for when we push sigma really a bit too much. And then the second point, as I said, was that we wanted to, in fact, compare the data efficiency of Metropolis-Hastings compared to backprop here in this case. And this comes from a lot of discussion that we see, quite recent discussion that we see in the deep learning community, where it has been shown indeed that Bayesian techniques for training neural network basically require less training data in order to achieve kind of similar test accuracy. And it is often argued that this comes from the fact that Bayesian techniques are better at basically balancing the overconfidence and underconfidence of neural networks. So this is shown here in this example here. Basically, you have a binary classification problem, and we see that the system here on the left side that was trained using backprop, indeed will learn a hyperplane that separates well the two classes, but the output of the neural network is always overconfident, even if you're kind of outside the domain where you saw training data. But quite interestingly, the authors here showed that when you use a Bayesian kind of learning technique, such as, for example, incremental kind of Bayesian learning, what you will see is that the confidence of the neural network will be high in the places where it has seen training data, but let's say will be more moderated outside. And so this is often argued to be really kind of an indication that they do a better job at, let's say, balancing kind of overfitting and underfitting, and therefore leading to better data efficiency. We also observed this in our spiking neural network case, where we see that basically the Metropolis-Hastings technique achieves, in fact, plus 10% accuracy when we use, for example, here only 25 training data points compared to the backprop case. So we see clearly that it basically requires less training data in order to achieve good test accuracy. And this, in fact, holds across the kind of SNN non-ideality degrees, which is also interesting as well. So I'm at the conclusion now. So in this work, as we saw, we have investigated the use of Metropolis-Hastings as a kind of alternative way for training spiking neural networks in a model-free manner that could be used in chip-in-the-loop kind of setups. We saw quite remarkably that the system allows you to have a better data efficiency as well, in addition to be kind of not affected by the hardware non-ideality degree, because it's a model-free approach. And this makes it quite interesting, for example, for the next generation of spiking neural network techniques that need to be, for example, personalized to different kind of patients in a healthcare kind of context, where perhaps you could reduce the number of data points needed to fine-tune your kind of very efficient SNN hardware to each individual patient. So thanks a lot for your attention.